So you can go from so if you want to represent it by this diagram, this how you can write iterative transformation. You can always go from this to this to this. So if you want to write it diagrammatically, so trace of this tau of psi is basically you can go from trace of n tau of sigma cross of trace of sigma of psi. So you can go in terms of this matrix tau to psi. So if you want to go from tau to psi, it is the same as if you are going from this to this and this to this. So going from this to this, a transformation going from this to this, it is the same as if you are going from this to this transformation and then this transformation to this transformation. So you are arriving at a given transformation via these two transformations. It will lead you to the same result. Yes, yes. And the relations can be summarized as, if you want to summarize this entire thing or entire procedure, this can be summarized as psi of k can be written as sigma I pi I k is equivalent to m tau of m chi of m k is sigma of I sigma tau of m omega m I sigma of k psi of k phi of k I tau of m psi of k chi of k m sigma of I and yes. So chi of mk can be written as sigma of omega mi phi ik So it can be written as this, it can be written as this, and omega L can be written as, and phi of ILK can be written as LM by LK. So you can see, so the question is, I'll write it. So in a triangle of transformations, we can choose the direction of transformation in such a way that we can choose so in a triangle of transformations, we can choose the direction of transformations in such a way that a set of expansion coefficients of second can be expressed in terms of third. So you can see it from there. Tau of sigma. So sigma is common, so you can write it in terms of third. So these two can be expressed in terms of third. So this and this transformation can be expressed as if you are going tau goes to psi. So the expansion coefficient tau in terms of omega and sigma, the expansion phi can be expressed as if tau goes to psi with these expansion coefficients. Now the point is, so this is the thing in the continuous case, and the reverse transformations can also be written in the so in the same sense there can be one is the homogeneous transformations, another is the heterogeneous transformations. So in the sense that once we normally talk of dimensions, we only talk of 1, 2 and 3, and if we talk of finite transformations, so if the transformations are in infinite dimensional space, so you can, there is no problem. You are mapping the transformations, infinite dimensional transformations to the infinite dimensional transformations. But if we have to specify the dimensions, then you have to specify it's 2, 3, 4, the number. Then only these relations can hold for the heterogeneous case. So you have to specify if it is 2, 3 or 4. So if you this sort of diagrammatics for 3, that expansion coefficient of the third can be expressed as the expansion coefficient of these two transformations. They get absorbed in the third one. So this can be, so if you have not only for heterogeneous transformations, for example, not homogeneous transformations, we can have the same sort of exercise here, in the sense that so if we choose we have a discrete so psi of x is written as sigma of I phi of x is equal to sigma of m tau of m chi of m x sigma of I tau of m omega mi psi of x phi I star x dx, and tau of m is psi of x chi of m star x is sigma of I omega I m. This is reverse transformation. Now, so you have written psi in terms of sigma and sigma in terms of tau, and further psi tau and tau in terms of psi and phi. So you can write tau psi of chi m. So you can have this thing. So if you again, the way we have written it for homogeneous transformation, if you want to make a diagrammatics for it, for if you have sigma, this is psi, this is tau, this is rho, this is zeta, this is zeta prime, so this is omega, this is omega, this is eta, this is chi, so you can have it like this. This is new, yes, yes, yes. Yes, yes, this is so you can have tau goes to sigma, sigma goes to psi, psi goes to, so you can have this. This is sigma goes to tau, tau goes to sigma. This is inverse transformation. Tau goes to psi. So it is the same. If tau goes to psi means first tau goes to sigma, sigma goes to psi. Tau goes to psi, through chi, but psi will come back to tau by chi inverse. This is inverse transformation. So you can go from tau to psi by a transformation through chi, this transformation. But if you want to come from psi to tau back, you have this inverse transformation. In the same way, you can see for psi to rho and rho to psi. Here psi and psi are inverse transformations. So this is a chart. This was for homogeneous transformations and this is for heterogeneous transformations. And the point is that how we can have these orthogonal transformations and whether they are homogeneous or heterogeneous, how we can see them. So if you want to for these again we can do the same exercise here also. The way we have done it for homogeneous transformations, we can do the same exercise here also, such that if phi of ik is equal to sigma, so the way we try to show it, if it's orthogonal in the previous one, we can do it for this thing also. If it's orthogonal, then and zeta k of L is equal to chi of k and eta L. So again, so we can write this here V of IL as sigma phi of k zeta of KL. So in the previous one there were two transformations, sigma I, sigma M. Again, so now we can have sigma k, so this will be equivalent to sigma k, sigma M, sigma N. So omega I m, chi of M k, chi of K n, chi of K n, neta of NL. So it will be equivalent to sigma of M, so it will be equivalent to chi of M k, chi of K n will be delta of K n. So that's it. And the way we have chart out there, if you want to write it for homogeneous transformation, if you want to just see this, because here it's sigma, psi, rho and tau. Here it was tau and psi also, but mediated through this sigma. So but for this thing, for two diagonal transformations, nu and chi. So this is one, this is chi, this is nu. So there are two diagonal transformations which are mediated, where omega im is sigma k phi ik, chi of k m, and the diagonal transformation goes through k m, phi of ik, chi of k m, neta ml. So it can be written as this trace of sigma rho, trace of let's see, if this is sigma and this is rho, so this is sigma and so sigma and this thing can be written as, you are coming from trace of n sigma of psi plus trace of n psi of tau into trace of n tau of rho. Again, so if you have to come from this to this, it means that you are going from sigma to psi, then psi to tau, then psi to tau, then tau to sigma. So the path is bit inverted. So to go from this to this via some orthogonal transformations. So we have an orthogonal transformations with given symbols. So you can always go from this to this. If you want to go from this to this mu, it is the same as if you are first going from this to this via some transformation, from this to this tau transformation, and then coming to back. So this is what it means. So basically, it's a sort of diagrammatics of how we can have these orthogonal transformations or unitary transformations via some matrix transformations by which we translate one space into another space, invariant space, or components remain same, but the space may be different, or the space remains same, but some matrix transformations, the components translate from one space to another space. And you can map from one to another by inverse transformation or adjoint transformations, which is called active or passive transformations. So this is the simplest way. So for homogeneous spaces, the simplest way can be how we can go from a given transformation, how we can via one or more transformations, how we can arrive at two transformations via other transformations in space also. For homogeneous spaces. For heterogeneous spaces, we have the thing of dimensions you have to specify. So this is another way of, this is the mnemonics or diagrammatics for the same of Arahimbatic. So it needs a bit of more, what I should say, facility or exercise of going through this, then we can enjoy it probably. Because it's little helpful how these transformations are there. In quantum mechanics, unitary transformations are very much used, and they just operate through matrix transformations, which are taken as operators, and how can relate one space to the another space, to the transformations from one space to the another space. So that becomes important as a tool also. So what are the philosophical implications? Will come by and by. What does it mean that some transformations they are invariant? Under certain transformations, things remain invariant, or they are symmetric, or under inverse transformations or reverse transformations, things should come where you started back, where you started, you come back where you started. So what do you mean by them? So we'll come to those questions in future. Thanks.